next to the third.
Okay, so yesterday we started doing a couple integration by parts problems. If you're watching the video, you might pause the video and attempt this before moving on. I'm going to go through it now, though they had some time to work on it. So, we need to select a UDV substitution, which we're going to learn where that came from next. But we just need to do it. Just executing the algorithm here. So if you were following along like last time, then the first choice you probably tried was u equals x squared for that part of the product, and dv is ln of x. And of course you could take the derivative of this, but we don't know the integral of that. In fact, that's its own parts problem, so we'll do that too today. So that's not going to work, so the only other obvious choice is this. Sometimes there's going to be 3 or 4 or 5 choices that you could possibly make, and you've just got to, try different things. Hopefully not too many most of the time. So if we take the derivative and find du, what's it going to be?
1 over x
dx.
Okay, sorry if I'm going too slow. But if I take the integral of dv, the integral of that's going to be
X cubed over 3.
Very good. All right, so now let's just see if that works. So we're saying this is equal to uv minus the integral of v du from our algorithm. And that's going to be ln of x. I actually want to write it like this. I'm going to go uv is x cubed over 3 ln of x. I kind of switched its places, cleaned it up, made it look nice, right? Minus the integral of x cubed over 3
1 times 1 over x
minus 1 over x
Ties appendix to student services, please.
So I think this problem also illustrates the fact that sometimes you don't just get dx, right? In fact, most of the time you're not going to just have dx, so you have multiple parts here. But is that an integral we can do?
Yes.
Yeah, I think so. We can simplify it first if we need to. Pull out the 1/3. X cubed over x is x squared. So this is going to be x cubed over 3 ln of x minus 1/3 x cubed over 3, so that's really over 9. Yeah, plus c. So integration by parts is one of those types of things where sometimes if you don't first succeed, try another substitution and try again, or look at the new integral you have and say, am I going to have to use parts on that again, like we did yesterday where we did it repeatedly. Okay, before we move on and try a couple more example problems, though, I think we should probably investigate where the heck this algorithm came from. And it doesn't come from a place that's too weird, really. It comes from a piece of machinery, calculus machinery, that you guys already know. There's so much stuff that comes from this particular piece of machinery in advanced math, differential equations. It's unbelievable. I mean, it's unbelievable how much stuff comes from this one idea. So I'm going to write this idea down, and I want you guys to tell me what it is. Paul, did you look already?
No.
So cheap. We'll look if we get stuck, but I don't think we're going to get stuck. Okay, and this also illustrates the need, in especially past Calc 1, to sometimes use Newton's notation, the primes, and sometimes use Leibniz in the same problem. I think that you really see that if you know both notations, it really helps out in derivations especially. So if I was going to take the derivative of this, what would I do? These are just two unknown quantities that I'm not thinking of them as constant. Just u and v are some kind of functions.
Product rule.
Product rule. And how would that go?
And the first times the second derivative, or so times v prime, right?
Okay, we can write it like that. Yeah.
Plus v times u prime.
Now, of course, you could also write it what other way. And it really doesn't matter. We're just trying to, clarify for ourselves. We could write this as what, Paul?
dv dx.
dv dx. Good. And this would be
du dx.
Now, I prefer Leibniz notation most of the time. It's really clear that those are derivatives now. I can't mistake what parts are derivatives and what aren't. It's up to you, though. Okay, so we had this, right? Let's bring down this. That's just the product rule applied to some u and v unknown quantity thingamajiggies. Yeah? But how the heck are we going to get from a derivative product rule into something that helps us with integration? you say?
Take the integral.
Brenna said, well, it's got to have an integral in it. So didn't we learn last year that you could operate with an integral? It is a type of operator. So if I operate on one side, I have to operate on the other side, right? Integrals are a type of operator. They are certainly not the only type of operator that you will learn if you continue in math. There's all kinds of other things, like things called Hamiltonians and gradients and lots of weird stuff. And I don't know a lot about some of those, so there's all kinds of things. Anyway, take a whole class in operator theory. So what would happen on this side?
D dx would go away.
It's like a cancellation, right? That's pretty obvious, I think. UV, all right. Well, what happens on that other side? And what should I really write with this? When I operate with an integral, what's kind of like a side effect part of the notation that always should be there?
dx.
I really should have put this, should I not? And then this is like a quantity dx, yes? And then since that's a plus, what can we do on this side?
Separate them.
Separate them. We know that's a property of integrals. You see how you can do this in terms of a proof, and we know all these steps are legal by something that we knew before. Yeah? So there shouldn't be any question. So this is u, help me out.
dv dx dx.
dx. Okay. And this one.
v dx.
Make sure you put like a tail on your u's when you're doing this so you don't like mix up u's and v's. Okay, just my advice. What you want. Okay. This is where I really liked writing it with Leibniz's notation. Can you see why now?
dx is canceled.
What's left?
Then you just subtract either one, really.
Because as you're Paul saying, do we agree that this is like a universally true statement as long as these objects maybe satisfy some certain properties? So if you took advanced analysis, which is like also called advanced calculus, which is a 400 level college class, they'd get a lot more into those. I think the book says, what's it say about the u and v? And it doesn't say much else. It says where both u and v are differentiable functions of x. So if u and v are not differentiable functions, which means they're also continuous, of course, right? So if they had like all kinds of asymptotes and stuff, this might not be true in some cases. But as long as they're differentiable functions of x, this is going to work always, okay? That's the condition on the theorem, or whatever you call it, yeah? But this is definitely universally true for that now, right? And we just manipulated it down until we got a tool we could use for integrals that could be written like this or like this. It really doesn't matter. It's just tradition that they subtracted this one over there. Okay, I mean, you really could have done it either way. Because now if we subtract that over there, we get uv minus the integral of v du is equal to what? The integral of u dv. And isn't that the original problem that you're supposed to start with? This is your problem that you're trying to solve. So if you can express something where you do a regular part and you put the other part as a derivative, and you do the algorithm we've executed, well, you know it's definitely equal to that by the product rule. Are we good? So that's where that algorithm came from. It's not a super mysterious place. It's just, hey, manipulate the product rule and it helps you do this kind of integral. Questions? You guys good? Okay. Let's do maybe two more, and I think we're all we need to do. Should we do that one with natural log, Sam? Just so we were trying to figure out, we didn't know before what the integral of the natural log of x is. I don't think you learned that in Calc 1. And the reason is, one way, or the easiest way to derive it, is integration by parts. That's why we didn't learn that integral last year. So things are done a certain way so that you don't get overwhelmed. So let's think about what we could do. U dv what's the weird thing?
We don't have a second.
We don't have a second function, but you could just call that second function 1, right? You could just pretend there's a 1 in there, and which one should be the natural log? Should it be this one?
Probably not.
Why not?
We don't know that.
That's what we're trying to figure out.
That's what we're trying to figure out right now. So obviously natural log has got to go here. We'll just put 1 there. Okay? So if we take the derivative, we do know the derivative of natural log is 1 over x. We do know the integral of 1 is x plus c, but you know we're not using the plus c as part of this. So we don't have to worry about the general family of solutions. And then let's just see if it works. And the whole goal, we don't know if it's going to work right now, right? Like we got that to work, but we don't know if it's going to work until the integral we get is something we can do. So we're going to say this is now equal to, so remember, you're saying this is equal to the algorithm because of what we just did. I used to, when I was in Calc 2, I used to just like do it. I didn't really think about it on a high level most of the time. I was like, okay, like I don't even know if I always connected that that was equal to what I was doing, but it is, right? It's the whole point. Which anyone should recognize, but I don't know. So uv is ln of x and x minus the integral of v du. Oh, and I should have a dx here. Shame on me. Huh. And the integral of that again is
X.
x. I did remember it right. I said plus though, didn't I? So that's a good one to memorize, but I don't know if you have to. Just do integration by parts and leave it. Okay. Let's do one more problem, okay? And there's an application in this section called centroids. We're going to do centroids in a couple weeks here, and then I'll go back and give you some centroid problems from different sections. I meant to do it last year, but it's the one thing we didn't get to that I wanted to. So another time, a week or two down the road. Okay, I think we've covered everything in here. Do you guys need to see one with like a definite integral?
Why not?
I don't want to do that one.
Never mind.
Let's do this one. I'll change it though. So let's do secant cubed of x. This is a little variation on our problem. You guys can try to help me, okay? So look at the book.
You say don't look at the book?
And the answer is going to have like secants and tangents in it, so I'm going to pick what would be good integrand, what would be good limits of integration to go from. Secant of 0 is undefined, isn't it? Is it? Cosine of 0 is 1, so it's not undefined.
Because it's at the, because of index 1.
So that will work. We could go from, and tangent of 0 is 0, so we're good. Let's go from 0. What would the...
Pi over 2, maybe?
One of those is undefined. Secant is undefined at pi over 2. Let's go like pi over 3. I bet that'll work. I bet we get a solid answer out of that. Okay. Let's hope. So, integration by parts.
Secant cube?
Secant squared
Or
is
you
something.
could do secant squared and another secant.
Yeah, I don't remember what secant
You guys hear
is.
Paul?
It's like tangent, the derivative of tangent or something.
Yeah.
So this is another time, just like that last one. I don't know if you want to just chuck secant cubed into here. What these guys are saying is, for those watching the video, is maybe you should peel off some of those secants, and that's also going to be useful for other integration techniques we do. So how many should we peel off? Well, probably just one. But you might have to experiment on some problems once again. If it's like 5th or 6th power, you might have to pull a certain number off. Paul's saying secant squared is a good thing to pull off, or at least have in there, because
That's the derivative of tangent.
that's the derivative of tangent. So where should I put the secant squared?
dv.
Aha. Does that make sense to you guys? Now, you know, Paul came up with that fast through, you know, he just thought about it and came up with it fast. You might have to try a couple things before you get there. You might not know, you can just plug things in and try it. Once you try a couple things though, I bet you guys will get it. So, this is now what? Tan x. That was the big insight in this problem. There's two insights, I would say. That's number one. So what are we going to put here then? We have to put secant. Do we know the derivative of secant?
Secant tangent.
Secant tangent. Thank you. Okay, so I think we're good. Let's just see what happens. So this is now equal to, oh wait, let's not write it again. Let's do the actual thing. So uv, secant tangent, is that right? Minus the integral of v du. Oh, I missed my dx again. Dang it. dx's shouldn't just appear places. You should know where they came from. They can come from integrating an equation on both sides like we just saw, or they can come from the natural consequence of taking a derivative or differential, right? It shouldn't just be like coming out of nowhere. All right, so so that's what? Tangent squared and secant. And we do that integral.
Do you have to do parts again?
It's a good idea, but no. If you do parts again, you're going to get into an infinite loop. And you don't want to do integration by parts out to infinity, I'm guessing.
Not really.
There's an identity that's useful here. Do you remember secant squared and tangent squared had an identity like sine squared and cosine squared? You might not remember it precisely, but there is one. Look it up. We will need to memorize those identities this year, or at least be able to derive them. For instance, am I going to have to look this up if I forget? No, I'm going to write sine squared plus cosine squared equals 1 and fudge around and say, you know.
1 plus tangent squared equals secant squared.
Okay, so the golden identity that we need here is 1 plus tangent squared is secant squared. Where'd that come from? It came from sine squared plus cosine squared equals 1 and dividing by something. Yeah, so if you ever forget that, I always am prone to like put the 1 on the wrong side or something, like -1 in the wrong spot or something, you know, make it very close to the real thing. So I usually check it if there's high stakes involved, like a test. Okay? But anyway, that's the 1. So what can I do here then? I can say,
Subtract 1.
if we go like this, then that is there.
And then you put secant squared. X minus 1 times.
Right. And there's another secant out here. Now you're saying, maybe I need to do parts again still, right? Integral.
Now, is that integral still from 0 to pi over 3?
Yes. I should have it all the way through. You guys hear Paul? He said that these limits of integration should be on all of these. Being lazy. Oh. So, do I need to do integration by parts again, or can I do something clever? You might be successful with integration by parts again, but I would doubt it. It might work. This problem is called a wraparound problem. How about if we just distribute? Can we do that one?
Yeah.
It was one of the hardest integrals we learned last year. Probably the easiest to forget, but yes, we know that. Can we do this one?
That's what you had back up there.
So this is what we have. Let me write it clearly for you if you don't see it. this is all equal to the integral of secant cubed, right?
So the cube.
So,
Congrats.
wait, is that, I think it's plus secant of x.
Let's do this first. Do you guys remember this one? I bet you forgot. What's the integral of tangent? I think it's negative natural log of cosine? Something like that? Those are the easiest ones to forget. They're not very common.
Sounds good.
Look it up. It should be in the front of your book, right? Let's check real quick. Let's check. So the integral of tangent is...
Is negative natural log of cosine.
And remember, that came from doing a simple u substitution with sine over cosine, yes?
Yep.
This one was trickier. I gave this as a big challenge to you guys last year.
Natural log of secant plus tangent.
It's the natural log of secant plus
I
tangent.
think it's positive because when you
There's a
distribute,
minus right there, though.
when you distribute the -1.
Oh yeah, you guys see it?
Mm-hmm.
That minus and like that positive. Thank you, Paul. And the actual integral is positive too. Good. Thank you. Very nice. But see, now the thing that we have here that you've got to recognize is there's an integral of secant cubed on both sides. So I heard Alexa say, hey, you can just move that over there, and there's 2 of those, and then you can just divide by 2 and you have your answer. And that's the answer. So we can just say, move that integral, this one's done, right? Over here. Have my dx's, darn it. And now there's just 2 of those. So what we have is 2 integrals of the secant cubed. And then we have a whole bunch of stuff we finished over here. Secant x, tangent x. And we have our plus natural log thing. Yep. And we have a plus c. So the only thing left to do is, hey, we didn't want 2 of those, the integral of 2 of those, we wanted just the integral of that. So that needs over 2, that needs over 2, the c can absorb the other 2. Okay, we can just call them different c's. Are we good? So I think that's about as hard as the problems get in this section. There's probably a few that are a little tougher than that, but you should be able to get them from that, I think. Okay. Any questions?